Thank you for the introduction. So I'm going to speak about a new thing we plan to implement in Rocq, which is ghost sort. So this is a very work in progress, and we'd love your feedback if you have any. Okay, so I don't know how many of you in the room have already used Rocq's extraction mechanism, and how many of you have already been annoyed by useless arguments that have been extracted and that unnecessarily slow the code, right? So with this ghost sort, what we do is that we take care of these kind of inconveniences of the extraction, and all of that using a single annotation, right? So for instance, let's say that you want to define lookup function with you want to look up to an index in a list. So there are more or less two ways of doing that. So the first one is to have monadic programming with saying if the index that you request is greater than the length of the list, then you return none, and otherwise you return some object. But you also have the logical justification using this fin type, which basically says that the index that is given should be lower than the length of the list. And in this case, when you match on the list and you get something empty, then you have a proof that something is lower than 0, which means that it isn't possible, and you discard this dead branch of your code. So what happens when you extract this code is this OCaml code, which has two useless arguments in the constructors of the fin type, because, well, these are the arguments that are actually used to logically justify that fin 0 is empty, right? So with only the ghost annotation here, we would like to extract something like this without these useless arguments that aren't actually used in the code, right? So, but this, well, this will be great, but there are like some kind of problems with indexed types, like the vectors. No, sorry, yeah, okay. So what happens here is that, yeah, before we had this fin inductive, which basically said that you can't inhabit fin 0 by using this natural number. And yeah, it extracted with the natural number as argument of the constructor, right? And with the ghost annotation, we only get no natural number in the constructors of the extracted code, and we get something that is kind of like NAT. So maybe we could extract to something like this even, right? So yeah, but as I was saying, yeah, we have some kind of problems with indexed data types. So for instance, vectors, where we can define this length function of a vector to simply return the natural numbers that is inside, that is the indexed type of the vector, but which means that we actually use this implicit argument. And so when we extract it, we actually don't look at the vector, and well, we have an implicit argument and as an explicit argument of the function. So it's not good at all. And what we would do with the ghost sort is to actually have the fixed point to compute the length of a list, of a vector, sorry. And so when we extract it to camel code, we don't get this natural number inside the arguments of the constructors. And we also have, we forget them here, and we actually have a function. So, but this thing may remind you of another inductive type, namely lists. So maybe we could do something like this, right? So yeah, what happens is that previously in Rocq, we had this kind of cohabitation. We had like two sorts, the prop sort and the type sort. And what we did was that in the prop sort had strict propositions and non-strict propositions like accessibility or equality. And we broke up this prop universe to two sorts, the sort of strict propositions and the sort of propositions. And so the ghost sort is kind of a similar refinement, but for the type sort, where here we want to break up between proof-relevant content and actual computational content, right? So what would happen is that we would break up these two things and get something with a hierarchy of ghost sorts and of type sorts. So but you'll tell me that okay, you present something which you want to be erased at extraction, but isn't that already what prop does? Well, actually, yeah, but we have a few more things. So yeah, first, of course, we get the erasure at extraction. That was the goal of this sort. We accommodate hack with using the same justification as the one in prop. And we have consistency. Well, prop is assumed, but here we have a consistency by saying that we can actually interpret ghost as type and yeah. But we can also prove in ghost that true is not equal to false, which is not something that we can prove in prop. And so we can actually have natural numbers in ghost. It makes sense. And so this is kind of this indices erasure that we get because we can actually have indices in ghost and erase them at extraction. The only thing we lose with the ghost sort is the impredicativity that the sort prop has. So we still have multiple designs that we consider for the ghost sort. So the first one is that ghost only has large elimination on false, but it would mean likely a redevelopment of the logic inside the ghost sort. Except if we wait for a sort polymorphic one, which will be arriving soon also. The second design would be to have ghosts eliminating into SPROP. And then we could use SPROP logic and ghost elimination inside proofs for strict propositions. And the third design we consider is ghost eliminates to prop. And this is the most comfortable one because we could actually use it kind of everywhere in the proofs, easy justifications. Okay, so these are the designs that we currently consider, but all of the things that I've presented before still hold for any of these designs. But yeah, what we are currently planning to do is currently we have some examples with the different designs, even though it takes a lot of time to develop each one. So we want quite a few more. Yeah, what we want to focus on is MetaRocq formalization to prove this erasure theorem, which says that, makes this diagram correct. And then once we have this, we'll make an actual Rocq implementation of this ghost sort. So yeah, there are already some kind of things that resemble ghosts in the literature, notably quantitative type theory, which is implemented in Agda. And yeah, which is quite different because it actually, we actually have the information of the number of uses of a term in quantitative type theory, whereas we don't have anything of the sort using ghost. But erasure can be explained using this annotation saying that T is never used at runtime. Even though, here, comparing, using ghost sort, only the eliminated rules have to change, whereas implementing quantitative type theory is much harder endeavor. And lastly, as far as we know, the quantitative type theory doesn't have erased accessibility, while we do. Finally, there is this erased modality that has been studied a bit by Niels Sanders Danielson. And we have quite a few properties that we also satisfy using the ghost sort. So notably that it's a monad. We can define stable types if we have an erased A, then we can get an actual inhabitant of this type, and the revival as equivalence between erased and not erased type. And so, yeah, we can do something like this in Rocq, which is a bit ad hoc, but we actually satisfy these things also. So to conclude this talk, so this is a development plan of the ghost sort in Rocq. We are trying to formalize everything. We are currently implementing all the machinery needed at the sort system. And what we want to do soon is to settle for a design between the three I've presented you. And the preferred one currently is ghost eliminate to prop, because it would allow to, instead of having a ghost new sort, maybe we could say that ghost is actually type, and we could have an actual sort for computational content. But yeah, right now we want to focus on the formalization. So thanks for your attention.